We're going to just call this part 2 of this video since my little recording stand for my cell phone fell down during that last part. So picking up where we left off, we're talking about graphical. We always do our graphing notes in green, but we are doing a little color coding here. And we were talking about this blue, maybe car, how it had a steeper slope, so that told me it had a faster speed. Now there's one similarity to all three of these objects. All three of these objects have one thing that is similar. Do you see it yet? The thing that is similar is the fact that they all have the same starting position. Same starting position. And I'm going to be a little bit tricky and grab a fourth color pen. All right. Oh man, this starting position right here, that's a big deal. It's the same starting position. The same starting position throughout the whole thing. These observations about objects being faster or slower and then starting position, that's going to be a big part of our physics class as we focus on concepts, ways to describe physics with words, graphs, the way to interpret physics with just a simple graph. And then we're getting on to the part that maybe some of you love or maybe some of you don't love, the math. All right, so we're going to start off with just one simple equation, so it's really great. This is going to be our speed equation, where we have an x, a v, and a t. You might say, hey, wait, there's a fourth thing there. What are we going to put there? Nothing yet. So x is distance, and you notice that we had distance on the y-axis up here. And so first I'm just going to label the term there, distance. And then I'm actually going to take my green pen. I'm going to go back up to my graph that I was working on, and I'm going to put an X here because that is the symbol for distance. And as time goes on, we're going to use the X as our symbol on this axis rather than write out the word distance every single time. The units for distance are meters. In physics class, we will follow the metric system. And so we'll use things like meters, kilograms, and seconds to do some of our measurements instead of concepts like pounds or inches or even minutes. Now, V is for velocity, and I should have brought this up earlier, but velocity and speed are words that we're going to treat as interchangeable. Velocity and speed, we're going to say that they're basically the same thing. Now I want you to write both down because depending on whom you have as your physics teacher, they might put more of an emphasis on the use of velocity or more of an emphasis on the use of the word speed. Honestly, they both are depicting the same thing, and that's all we need to know for like our physics class. The units for velocity are meters per seconds, which I can write out, meters per second. Or I can do a quicker symbol version, m/s. And that makes sense if I think about maybe driving on the highway, driving on the Beltline. The speed limit is 55 miles per hour. And so that tells me that I can every hour, technically, if I set my cruise control to 55 miles per hour, I would travel 55 miles every 1 hour. Maybe you slow down to 35 miles per hour, and now all of a sudden you're going to travel 35 miles in that 1 hour. I wanted to bring in even just like a couple fun facts that do not need to be written down, but it may be fun for you to know. So when you're driving on the Beltline or on the interstate or maybe just on University Avenue, and you see things that say it's like 45 miles per hour, we might see it mph, but really that means miles over hours, much like our units that we're talking about in physics class. I just brought out a Sharpie. Of meters per second. Those have the same idea. Now, nobody ever writes like MPS for our meters per second, but that MPH, it just means miles per hour. Now, here's a fun couple of examples. If you're driving 55 miles per hour on the road, that's 24.5 meters per second. Usain Bolt, super fast Olympian runner from Jamaica. His top speed is 27.8 miles per hour. I think he's the fastest man in the world. Tell us if he's not. And that converts to 12.4 meters per second. And then I Googled slow turtles, and the leatherback turtle has a speed of 1.1 mile per hour, which is 0.49 meters per second. And again, you don't need to write this down or memorize this. This is just more fun facts as we continue on our way. Grabbing my red pen again, refocusing a little bit. The T stands for time. And time for us in physics class will always be measured in seconds. I'm going to take my green pen, I'm going to go revisit my graph up here, and I'm going to put a little S right here for seconds. Now hold up, I don't have anything over here for distance. I have this X here, but I don't have any mention of my units over here. It's meters, and I'm going to put an M to represent that. We'll do another graph practice so I can kind of clean this up a little bit in the future. Now, one thing to know about our physics class, we never, ever, ever will make you memorize equations. We'll never make you memorize things like is x distance or v velocity. We'll make sure we help you out with those in the beginning. And one thing we're going to challenge you to do is to try to memorize that distance is meters, that time is second, that velocity is meters per second. But I'll tell you right now that you're going to use those so much throughout this year that you will memorize them without even realizing that you memorized them. The last one here can be for our starting position. And our starting position is a distance measurement or a position measurement. And as a result, it is also measured in meters. Now, a lot throughout this year, the starting position will be 0. So you don't have to worry too much about that starting position. Now, direction matters, and we're going to talk about this a little bit throughout this unit. And when I say direction matters, what I mean is that you always will start at position 0. I'm sketching myself a little graph, and because I'm doing a graph, I'm actually going to make sure I get that green pen out. Perfect. So 0 is the origin here, where this car starts. If this car starts to travel what we've labeled as east in a positive direction, then that vehicle will be moving in this direction. But if we begin going in the opposite direction, maybe this car's reversing, maybe it's backing out of a driveway or backing into a parking spot or something, this is going to be referred to as a negative direction. And we won't see a ton of examples of these, but it's still good for us to recognize the difference between a positive direction, this going in a positive direction, maybe driving down the street, and a negative direction, which would be kind of going backward and away from the origin in the opposite direction. We're going to use this later when we talk about free fall. We'll actually reverse it, and we'll say anything that's falling travels in this negative direction downward. But that is for a whole different unit. Let's go to the next page of our notes. Page 3. Now, it's at this point that you might say, geez, these notes are long. And I'll say, yeah, I agree with you. And that's why, if you came to class, if you can, these notes will be a little bit more quickly done, and you'll have that chance to kind of talk through them with your teacher. But if you need to watch the videos for your notes, that's a-okay too. Just realize that you are going to have to put in the time to make up for what you might miss if you came to class. So let's do an example of an object moving at a constant velocity. First thing we need to do is we need to make the graph here, and I'm going to get my green pen for the graph. And I'm just going to write out the position and time units to label my graph. We said time is always on the x-axis because time is always the independent variable, always doing the influencing. And I'm going to make my scale right away. I see I'm just going up to 4, so I'm going to go 1, 2, 3, and 4. Then I will stay with green, and on the y-axis here, we have position, sometimes labeled distance, and I can sometimes write it this way, but I think I'm going to write it this way instead. Units for position are meters. So I see that this is like 2, 4, 6, 8, 10. Let's check it out here. Can I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Ah, perfect. I can fit them on there. So I'm going to choose to just go up by 1s. Now, if you want to go up by 2s instead, that's a-okay. But your graph might be a little like smaller than mine, which is fine. I am going to use a different color because I like to. At 0, it's at position 2. Ooh. That's going to be important later. At 1 second, it's at position 4. At 2 seconds, it's at position 6. At 3 seconds, it's at position 8. Oops. And at 4 seconds, it's at position 10. Nice. Ooh, look at that. Now, we do like it in our physics class if you connect the dots in a nice best fit line. We don't need you to connect the dots like it's a constellation in the stars. We just rather you make a line of best fit. That's a math term that hopefully you're familiar with. And most of the time in this situation, that line of best fit is perfect because our data is linear. So let's go through these little questions we see right here, right now. So graph the data and the position time graph to the right. Check, we did that. What does this graph tell you about the motion of the object? Well, we've got a linear line, so it's moving at a constant velocity. I'm actually going to switch over and grab my blue pen because we are doing some concepts here and making some observations from the graph. So I grabbed my blue pen. What is the starting position? Ooh, I have 2 places that I can observe that starting position. I can see it in the table at time 0. It was at 2. But I can also see it in the graph. Check it out. At time 0, it was at 2. So no matter what, the starting position is 2 meters. Using the slope triangle, find the slope of this line. Now, I have heard in the past that slope triangle is something you guys do in math class. You do rise over run, and so you go rise, and then you've got run, and you make a triangle here. I've heard that's something you've done in math class. And with your slope triangle, when you do that for math class, you take So in that slope triangle, you take y2 minus y1 over x2 minus x1. But, we're not going to deal with those x and y axis because we've got labels. And so what we're thinking about is position 2 minus position 1. Or really, x2 minus x1 all over time 2 minus time 1. So I chose 2 random numbers here. Let's see, position 6 and position 8. So we've got position 2 is 8 minus position 1 is 6 all over. Okay, well, let's see. What did I choose for my times there? 3 and 2. So time 2 is 3. Time 1 is 2. 3 minus 2. Okay, and I do want to take a quick moment and grab my red pen because, oops, this was math all along and I forgot. And let's see, we have 2 over 1. Beautiful. But what are my units again? Let's think about it. This was asking me to find the slope of the line. And if I remember on my previous notes, what does the slope tell me? It tells me the speed. And what is speed measured in? Meters per second. And check this out. Position measured in meters. Time measured in seconds. That follows all the way through. So I have 2 meters over seconds. Meters per second. So let's look at question number 5. Based on the answer to number 4, what is the velocity? It's 2 meters per second. Oh, we did it. So now it says that using the equation x equals vt plus starting position, what would be the distance that the object travels in 10 seconds? Well, we're new to this math game right here, and so we're going to do this together. I have x, I have v, I have t. And I'm going to do something new that maybe you've heard of before, but I'm going to use the guess format, G-U-E-S-S. G stands for givens. U stands for unknown. E stands for equation. S stands for substitute, and the other S stands for solve. Now, these 5 sections here are very important, and most of our math questions are actually worth 5 points, and we give points for you doing every single step of this question along the way. We'll do a ton of practice with this, and we'll do a lot of examples, but I want you to know right now that every single physics teacher really cares about you following that guess format. None of us are really impressed if you can do all this math in your head and just write down an answer and move along. We want to see you follow that guess format. So we're going to do that together. I'm grabbing another color pen because one thing that you'll learn about me is I really like Flair pens in all the colors. Who's with me? Loves the Flair pens. Moving along though. So, X. Well, it says what would be the distance at 10 seconds. So right now we don't know X, and that's actually going to be my question mark. V is the velocity, the speed, and I've got that right up here in my question number 5. So I'm going to put a 2 meters per second there. In a perfect world, these would be lowercase, but it's okay. T is 10 seconds, so I'm going to put 10 here. And what was my starting position? Oh, yeah. I could tell in 2 different places, and it was 2 meters. All right, cool. Well, so I already had the equation written for me, which was convenient. I'll tell you, honestly, in the future, you've got to write that equation. And if you don't, you lose a point. That showing of the work is an important thing that you'll see everywhere in your life, and we'll talk about it more. Substitute. The substitute part I sometimes like to call plug and chug. We're going to take these numbers and we're going to put them into this equation. So we've got x equals v is 2, t is 10, plus 2. And it's at this point that I say, rats, why am I not using that red pen again? So grab your handy dandy calculator and you do 2 multiplied by 10 to get 20. And then you add 2 to get 22. What are the units again? Meters. Whew. Love it. You should pause the video here and maybe go through this one more time if you need the practice. If you don't, awesome. So I've flipped over page 3, and now I'm looking at page 4. Last bit of notes for us. Thanks for sticking with me this whole time. This whole section is graphing in green. And, well, I told you I love the Flair pens. I got 2 different colored greens here. Lucky me. I might also throw in some orange later just for fun. Okay, so let's look at these graphs right here. We're focusing on our 3 ways that we can communicate physics. We can communicate physics with graphs. Oh, we've been talking about that a lot, and I'm really pumped about my different color pens. We can talk about it with math. Oh yeah, give me that red. And then verbal. Conceptual is another phrase we might use there, and that is blue. So let's start with our verbal wordage of this. It says Wayne is biking in a positive velocity. Oh, remember that? That was this thing here, moving one direction or the other, a positive or negative. That's going to revisit itself. So a positive velocity of 5 meters per second and its starting position is 0. Ooh, convenient. Well, I'm going to follow the logical order and do graphs next. First things first on this graph, we need to label our x and y axis. We've been saying before that time is on the x-axis, measured in meters. So I just put 1 t there with the meters. And then our y-axis is actually distance, measured, symbol x, measured in meters. And oh, look what I did here. Did you do it too, or did you say, wait a second? What's Miss Humphrey doing? That should be seconds. All right, starting position is 0. Grabbing my green pen, putting a nice healthy dot at 0. And he's going to move at 5 meters per second. So I'm going to be just nice and easy peasy, and I'm going to label this 1, 2, 3, 4, 5. And that's 0. And if I wanted to, I could do 1, 2, 3, 4, 5, but that would only get me like 1 data point. So that's not really convenient. So I actually think I might just have this go up by 5s. Now, when you're doing this on your own work, don't forget that you're making these scales here for your graphs. So 1 second goes by, it's traveling at 5 meters per second. Second goes by, it's another 5 meters. Third second goes by, another 5 meters. Fourth second, fifth second, and we see that linear line forming right there. Nice. Now the math. Activate red pen. So for our red pen, what we see here is x equals the velocity. What is that velocity? It's 5 meters per second. How could I find the velocity on the green graph? Do you remember? Do you remember what is the velocity from the green graph? I'm going back to page 2. It's the slope. That was our speed. We almost forgot to acknowledge it. Our speed is the slope. So we know, though, that that velocity is 5. And the starting position is 0. And so then we'd be ready to do some math, whether it be how long does it take Wayne to bike 50 meters, or how far does Wayne bike in 45 seconds, whatever we choose. Let's move on to the next question. Ooh, Sarah here. All right, I'm going to look at what information I have. I don't have blue stuff yet. That's labeled. That's blank. Red stuff is blank, but my graph is telling me some information. First things first, label that graph. So time in seconds, position in meters, and this is always 0. And what's exciting is it doesn't really give me any information about what I'm even looking at. I noticed that Sarah is running in this one. Now I did a quick little bit of research, and I found that 10-minute mile, if you want to get a 10-minute mile, you have to average 6 miles per hour, which can turn into 2.6 meters per second. So just to keep our numbers like legit here with Sarah, if she needs to run like a 2.6 meters per second, I'm still going to do 0, 1, 2, 3, 4, and 5. And I'm going to make my distance here 1, 2, 3, 4, and 5. And so what I'm seeing is as 1 second's going by, she's traveled about 2 meters. Second's going by, she's traveled about 2 meters. She's got a really nice stride. She's a good fast runner. And yeah. Now going away from like this little stats I have here, let's focus on what we see. Starting with, I love to do conceptual first. So I'm going to activate my blue pen. The starting position might be the easiest thing to do first. It's at 5 meters. After I do that, I can find the slope of this line. Well, I can use my slope triangle, can do rise over run, and sometimes I'm just like a little bit observant. So rise, or in this situation, lowering. Rise is 2 meters. And run is 1 second. So I see that it traveled 2 meters in 1 second. So that tells me it's 2 meters per second. Now, I personally am a little bit like to get quick with this stuff. And so if I would have documented the 5 meters as the starting position first, sometimes I then pop over to my math and throw it in real quick. Okay, that's 5 meters, just so I have it for later. And then as I enter the velocity of 2 meters per second, I throw it in over in my table, hopefully remembering to switch my pens so that I have my equation ready. All right, let's do our last one. This is the last bit of notes. You guys have such good ability to stick with us this whole time. So now our math is given to us, and we're going to have to do the conceptual part, the words, and we're going to have to make a graph. So let's observe here. They tell us the velocity is 0.5 meters per second. Well, Garth is walking with a velocity of 0.5 meters per second. I dug that right out of the equation. And the starting position, well, it won't always be labeled with a handy dandy arrow, but right now it is. So we're going to put it right in there. So Garth is walking 0.5 meters per second with a starting position of 4 meters. So let's pretend it's a walking race and Garth cheated, moved up the line. Garth. Then I have our graph, which of course we should be using our green pen for. That should have probably been blue. I hope the color coordinating is helping you right now and not making your head explode. So I've labeled it time, which is in seconds. I've put a nice little scale on there for myself. This person's walking. So again, I think I'm going to just use a 1, 2, 3, 4, and 5 here. And it's a position on that axis, and it's measured in meters. Awesome. Now here's the one challenge. Is going to be really plotting out this graph. And I'm going to use my other color green for that. So it says it's 0.5 meters per second. So 1 second's going to go by, but it's only traveled 0.5 meters. So between there. Another second goes by, but it's only traveled another 0.5 meters. So that just gets me to 1. Another second goes by, and it's going to be at 1.5. Another second goes by, and we just made it to 2. Another second goes by, and it's at 2.5. If I draw that line of best fit, boom, right there. Really quickly, before we sign off for the night, I want to look at one thing. Look at these 2 graphs. I can make some conceptual observations about these 2 graphs right here. I'm going to think right now to myself, I've got 2 differences and 1 similarity between Sarah and Garth's running and walking. Look at that graph really quickly. Can you see what the similarity is? Can you see what the 2 differences are? I'm pulling out a purple pen for this. I see 1 similarity, linear lines. Those two linear lines tell me constant velocity. I'm going to write that down right here. All right. There's two differences, though. What are my two differences? Different starting positions and different speeds, different slopes. So Sarah's obviously running faster, and I can see that because her slope is steeper. I also see they're traveling in different starting positions. And uh-oh, did anybody catch the mistake I made on this graph here? I just saw it right now. The starting position was supposed to be 4 and I made it 0. Oh no. Rats. That was a legit mistake, not a desired mistake. I'm really sorry if you did that and you were confused. This was an okay mistake to make. So, really, folks, friends, oh man. That right there, that's your desired graph. That one right there that I've circled in orange. And even I might go like that. I hope that if you had used a pencil, you could just erase it. And you can just cross it out like me. Have it be like a little Bob Ross happy mistake. But still, the slope is the same because the speed is the same. Maybe that's a good takeaway. Anyways, yep, different starting positions. Yep, different speeds. Ooh, there's one more difference though. Direction. We see that Sarah is traveling in a negative direction. So maybe she's running back to her house because she forgot something. And Garth is traveling in a positive direction. So he's running to school away from his house. Let's document those differences and let's call it a day. I'm left-handed, so I'm going to turn my paper just a little bit. So I had 3 differences that we decided. We had starting position, we had speed, velocity, and we had direction. Awesome. Have a great night.